So we're gonna kind of start over. A whole new way of plotting points in graphs called polar coordinates. Here we go. So polar coordinates are not based on horizontal and vertical position or rectangles, right? So it's called rectangular coordinates because horizontal and vertical position are like at 90 degrees to one another. But instead, it's based on two different variables. So the first variable it's based on is angle. And this is the standard trig angle swept counterclockwise from the positive x-axis. Okay, so this should be familiar, right? So the standard trig angle swept counterclockwise from the positive x-axis. And what if we go clockwise? Then what about those angles? Negative values of the angle, right? So if I started sweeping clockwise, then it would be all the same. It would be the same thing, but it would be the angles would be less than 0. Okay, so that's our first way of locating points in the polar plane is by the angle. And so then once we pick an angle, once an angle is established, say here, this is the angle 2.67 radians. And what does that mean? So how do we get the number 2.67? Why is this angle 2.67? Anyone learn this in trig? 2.67 what? 2.67 what? Andrew. Hold on a sec. Andrew.
Radians.
Okay, what is that? What are radians? What is 2.67 what?
It's 180 degrees divided by 5.
Okay. So that's not really the meaning of radians. That's kind of how you would like transition between radians and degrees. What are radians?
Radian is the central. Sorry, is the. Gosh, you just said this. The radian is the arc of the circle equal in length to the radius of the circle. Sorry, it's the angle of the circle sustained by an arc of the circle equal length to the radius of the circle.
Okay, and what does that mean? Sounds like you memorized something.
I did memorize.
And what does that mean?
It means that the arc length.
The arc length.
Of the angle is equal to the radius of that circle.
So, okay, what's that? 2.67 times the radius. Right, so if I picked any circle here, I could pick any one of these circles. Say I pick this one right here. Oh no. Okay, so if I pick any one of these circles, say I pick this one right here. I gotta turn it. So say I pick this circle right here. So, and what do? We swept an angle. So right like that. So that circle has a radius right here, like this is the radius, right? So what does it mean that this angle measure is this is 2.48. I've got it at 2.48 radians. It means that this arc length is 2.48 radii long. So if I took this radius right here, this distance right here, and I wrapped it on the circle, it would take 2.48 of those radii to sweep out that angle. And if I choose a bigger circle, this one, that has this radius. Is it a different angle? No, it's the same angle because now if I take this radius of that circle and lay it on the circle, it'll still take exactly 2.48 of that radius along this circle to get the same openness that I've swept out there from the positive x-axis. So that's what the number 2.48 means. It means how many radii, so if an angle is like, angle has to do with arc length, right? So it's how many radii of that, of the circle that has that arc fit along that arc, right? So here's the blue radii, 2.48 of the blue radii fill up that arc. And here's the red radius. And 2.48 of that red radius fills up that arc. So that's why this angle measure is 2.48 radians. 2.48 radians, okay? So that's the first coordinate. Radians, or angle measure, is the first coordinate that we look at in polar coordinates. All right? So then, once we have an angle, then now the terminal side of that angle, so pointing up and to the left there, that is the direction of positive change, or positive change. And so now that coordinate is now distance from the pole. Distance from the pole. So you have angle measure, and then once you establish the angle, the terminal side points in a direction away from the pole, and along that terminal side, you measure distance from the pole, and that's called R. So the R value is distance from the pole in the direction determined by theta. Yeah.
Is the pole the center?
Oh, pole. Yeah, pole is this. This is the pole, right? Sorry, this is called the pole now. It's no longer the origin. Before, where the x and y axis crossed, that was the origin. This is now called the pole. Think of it like you're looking down on the top of the earth, right? And so that's like the North Pole, right? So this point right here has coordinates. Now you would think, and it makes more sense that it would be theta comma r, but for some reason they put r first. But the way we want to think about it is theta comes first. Theta comes first. So 2.482? So 2.482 radians. Oh. Nacho, could you hand these out, please? So 2.48. So we sweep 2.482 radians counterclockwise from the positive x-axis, and then I chose. So this point right here then would be r equals 3. So that's the point. 3 comma 2.482. But the way we want to think about it is that the angle measure comes first. 2.482 comes first. No, that's distance, right? It's whatever your distance unit is. So this is a distance unit, distance along here. Yeah, so it could be, it could be whatever your, just like in the XY plane, it could just be a non-dimensional, or it could be like feet, inches, miles. So this is distance, right? Distance from the pole. And then this is angle measure. Okay, questions so far? All right, so then we have to know our angles, right? So you remember when you learned your trig, we learned some key angles, right? So how many angles are there from 0 to 2 pi? How many angles are there? There's an infinite number of angles, right? So we got every single possible angle in there. But there were like key angles that were based on symmetry of the circle, right? Based on symmetry of the circle. And so let's just review those. So how many? Of course it doesn't. So I say A equals. So how many, to get exactly halfway around the circle, how many radius lengths does it take, right? Or what is the angle measure? So how many radius lengths does it take to get exactly halfway around the circle?
Pi.
Pi. That's where the number pi comes from. If you take pi number of radii, it gets you exactly halfway around the circle. So let's just do that. Right, so this is, so even like looking right here, so that arc length right there is 3.14159 yada yada yada, number of radius lengths of that circle, and it takes you exactly halfway around. Okay, so this is our angle pi radians. So then, to get to the top of the circle would be 1/4 circle, right? Exactly 1/4 circle would be how many radians? Pi over 2. So this is no longer the y-axis, right? There's no y-axis anymore. It's going straight up from the pole. You're talking about the angle measure pi over 2. It's not y. It's not y anymore. Okay? So then going 3/4 of a circle would be 3 pi over 2. So what is the value of 3 pi over 2? 3 pi over 2 is 4.71. Tell the person next to you, what is so 3 pi over 2 is 4.71 something. What does that number mean? 4.71. What's the importance of that number? 4.71239. Tell the person next to you. Go. I don't have any more. We'll have to share. They're just blank axes. Okay, so what did they say? 4.71? 4.71 means what? 4.71 means what? Yeah.
4.71 radii will get you to 3/4.
Right, so if you took a circle and you took its radius and you laid it along the circle, 4.71 of those would get you 3/4 of the way around the circle. So 3 pi over 2 isn't just the name for that angle. It's just not a name. It's a number, right? 3 pi over 2 is a number, 4.7, meaning that if you took 4.71 radiuses and laid them on the circle, it would get you 3/4 of the way around. That's how we get angles, right? Angles is by taking arc length and measuring the arc length with the radius of the circle. And that's where angles come from. Okay, so then we have 2 pi. Let's just write these down. 2 pi again. 6.28, yada, 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 is how many radius lengths it takes to do one full circle, right? That's what that angle measure means. We start here at 0. So then we can just start dividing these up with symmetry. So pi over 2, half of that is pi over 4. And then halfway between pi over 2 and pi is 3 pi over 4. What's this one? Halfway between pi and 3 pi over 2 is 5 pi over 4, etc. And then 7 pi over 4. And then we can take each quarter circle and we can break them up into thirds. So pi over 2 divided by 3 is
6.
pi over 6. And then 2 pi over 6 is pi over 3. Okay, and then we got 2 pi over 3. So this is 5 pi over 6. 7 pi over 6 is down here. So now I included a couple more in there that aren't, let's see, so 7, 9, 8, 4 pi over 3 here. Then 5 pi over 3 down here. And then 11 pi over 6. So these are what we call the 16 key angles, right? The 16 key angles on the unit circle. And so then these missing ones here are not part of the 16, but this is what pi, this is pi over 8, and then pi over 4, and this is 3 pi over 8, etc. So there's some in here that you didn't memorize back when you did calc, these red ones. Those are pi over 8s, okay? All right, so that's just a quick review of your angle measures. Every one of those, that's not a label for a position on the circle. It's a number, right? You could divide pi or by this fraction and you'd get a number, right? And then that number would be how many radius lengths it takes around the circle to get there, to get to that, sweep out that arc or that angle. Okay, so now notice here I'm at my angle right now that I'm showing is 3 pi over 2, right? 3 pi over 2. And so then that gives you the direction of, so this is negative, right? R is negative going down, right? No matter what your angle is, no matter where the angle points, it's pointing in the positive R direction. So notice these are still positive. So this, what is this coordinates of this point right here? Coordinates of that point are 2, comma, 3 pi over 2. Not negative 2. Not negative 2. So you sweep, and then that terminal side always points in the direction of positive R, no matter where it ends up. Okay? So this is positive 2. Yeah?
Does that mean that R will always be
No. Hold on a second. So we do have negative R, just haven't gotten there yet. Okay? But we got to make sure we got that, we have that much down. Notice, as I increase the angle theta, that axis stays with positive values of R, no matter how far I sweep theta. Even if I'm sweeping down, even if I'm sweeping to the left. Okay, so then she asked the question, is there negative R? Is there negative R values? So let's go to this one right here and say, what angle is that right there? So what is theta here? It's one of our key angles, one of our 16 key angles. This is pi over 3. This is pi over 3. And so then what would a negative value of R look like? This is where it gets confusing for students. So this is the angle, positive pi over 3. And you see where the positive R values are. They go up and to the right. So where would negative R be? Right, exactly what? Pi radians in the opposite direction. So for pi over 3, here is where a negative R axis is, right? So here's the negative, maybe. Yeah, there it is. So there's the negative R axis for pi over 3. All right, so what are the coordinates of this point right here? So the coordinates of that point would be negative 4, positive pi over 3. If it's negative, so think angle first. Think angle first. We sweep out an angle of pi over 3. That makes the positive R direction up and to the right. So that means negative R is exactly the opposite way from that. So this point we could call negative 4 pi over 3, but this brings up another issue. Is there another way to write that? Yeah, Nick.
Would that be the same as positive 4 pi over 5?
So he's saying, is that the same as positive 4 and 4 pi over 3? Yes or no? Will positive 4 pi over 3 give me the exact same location in the plane? Yes. So in fact, for any given point in the plane, there's an infinite number of ways to write it, to write that, because we can have angles greater than 2 pi and less than negative 2 pi, and we can keep going around. All right, so in rectangular coordinates, that was not the case. If you pick a point in the plane, there's only one ordered pair, x and y, that will get you that point. But in the polar plane, there's many ways to write the same location. There's many ways to write the same location. Okay, so let's give you some practice here. Any questions on this? So remember, think theta first, then that terminal angle points in the direction of positive R. Negative r then is if you you turned around and started going the other way from that angle, from that terminal side. And then what about negative angles again? What was negative angles again? Not down, but clockwise, right? So if I started here at 0, if I rotated clockwise from there, all those angle measures would be the same in magnitude, but now less than 0 as we go around this way. Okay, so practice. So you got some blank axes there. You can practice, and I have a bunch of points here. Just go right to number 2. And so how do we think about this first? What comes first? Theta, right? So for some reason, the convention they give is r first. But the way we think about it, like the independent thing is the angle measure, and then the dependent thing is r. That's the way the functions are. The functions are that r is a function of theta. In fact, I didn't really say that. So when we have so before you start there, hold on a sec. So polar functions then, r is a function of theta. That's what we think about theta coming first. Okay? So and let me just show you one here. Okay, so check this out. So as you increase theta, then r is a function of theta. So here is, so there's some function here, it's this function right here, e to the sine theta minus 2 cosine 4 theta. So this is showing that when theta equals 0, what's the value of r? So we got our first point here is the point what? 1? 1, 0? It's not 1, 0. Negative 1, 0. Because when angle is 0, which way is positive r point? To the right, right? So when theta is 0, we got our positive r-axis this way. So if this is the point for theta equals 0, then that's at r equals negative 1. It's in the other direction from the direction of positive r. Okay, so then as you increase theta, you generate points according to this function, right? So this function tells you what r is for different values of theta. So so we started at negative 1, and now here we are at r is about, or the theta angle is about 1 radian, and we're about 3.4, r is 3.4. So this is the point 3.4 comma 1-ish. Okay, but all along there, as we increase the angle, we got different values of r according to this function right here, according to this function. So if we keep increasing keep increasing theta, it keeps generating r values. Are we positive or negative r right now? Positive, right? Wow, it's really touchy. Okay, so here we are at, what's the angle measure that we're at? Pi. Our value is negative 1 right now. So the angle measure is pi. R equals negative 1. So this is a very common type of polar graph. You get these like loops, like flower petals. So there's letting the angle theta increase from 0 to 2 pi, sweeping out all the corresponding r values. You get all this set of points. You get this set of points. Okay, so that's a complicated function, e to the sine theta minus 2 cosine 4 theta. We'll be doing easier ones. I just wanted to give you an example and cheer you up with a butterfly. Okay? All right, so you are working on points in the polar plane. So you're going to use the sheet that I gave you, and then but label the point. So after you make the find the point, then label it. So if you look at it later, you know you're. Requests A through F. Yeah, F. Okay, so F is both a negative angle and a negative r. So let me get this blue graph off the screen. Okay, so here's 0. So what would negative 5 pi over 6? Negative 5 pi over 6, we want to first figure out what's the positive direction of r that points. So let me ask this. What quadrant does positive r point in if you go negative 5 pi over 6 radians? You should be thinking third. Negative 5 pi over 6 is right there. This is the angle negative 5 pi over 6. And so which is the direction of positive r? Well, the terminal side of that angle, right? The terminal side is this. So this is our direction of positive r. But we want what? Negative 2. Negative 2 in this positive r direction, which would put us here, first quadrant right there. So that's the point, negative 2, negative 5 pi over 6. Does that help, Kellen? E, okay? Let's do this one first. All right, so everyone see negative 2, 5 pi over 6. And what would be the easiest way to express that point? What would be the very easiest way to express that point? What coordinate pair would be the most simple way to express that point?
1 pi over 6.
2 pi over 6. 2 pi over 6 would be the easiest, quickest way to express that point, right? Just up to pi over 6, positive angle, and then positive r2. But both of those coordinate pairs express that point. Does this make sense? Okay? You wanted E also?
Yeah.
So now E is a positive angle. We look at the angle first. So here's 0. Where is 7 pi over 4? What quadrant does that terminal side point in? Fourth, halfway through the fourth quadrant. There's 7 pi over 4. So the direction of positive r is down and to the right at the terminal side of the angle 7 pi over 4. So therefore, what's negative 4? 7 pi over 4. So this is, for 7 pi over 4, this is positive r. So where am I going to go? What quadrant? 2. So here's that point for E. Yes, please.
Given that there's an infinite number of ways to express these, is there a reason we don't just convert these all to like positive angles or positive sides?
Yes. So like if you're working with something complicated, like we're working with a function, we'll say, okay, let's make it just go from 0 to 2 pi or 0 to 4 pi. But then the function may give you negative r values, so you can't really avoid that, right? So your function.
You can only change one, right? You can change either the r values or the all positive or the pi values, radian values all positive, so that you're working in the same direction.
I'm not sure about that. Let's do that last example that I showed. So where did I? This may clear that up. I think I was. Was I here? And was the point that I gave you this one right here? When I said write it in 4 different ways? Okay, good. All right, so what's the most obvious choice? The most obvious choice would be the angle measure of 5, 5, or 6. And the R is 3.5. Okay, who came up with a different way to express this point? Dylan? No. Colin?
Negative 3.5 and 11.5.
So instead he's going to say the angle is 11 pi over 6, which is going to take us where? That's going to take us to here, and then negative 3.5. Did you get it? Right, so 11 pi over 6 means positive R points down that way. Negative 3.5 takes us back to our pointing question. Who has another way to do it? Yes, sir. Justin.
Negative pi over 6 and then negative 3.5.
Negative pi over 6 and negative 3.5. Does it work? Let's try it. So where's negative pi over 6? That's going down this way. So negative pi over 6, we sweep clockwise, and we're pointing this way, and then negative 3.5 takes us back here. Does it work? It works. So let's write that down. One more. Who's got another one? Said give 4. Chase.
Negative 7 pi over 6, 3.5.
Negative 7 pi over 6 and positive 3.5. Does it work? Okay, so did I confirm or deny your theory, Nick?
You confirm.
I confirmed. Okay. I heard you saying something like these had both be positive or both be negative, or I wasn't sure what you were saying.
No,
You're good?
There's a representation that has either a positive or a negative, either R value or pi value.
Right. You can make it so they're both negative. You can make it so they're both positive, one of each. Yeah. Okay. Any questions on points? Really important. So you can't do anything else in polar coordinates unless you understand really well how you get points in polar coordinates. And so you have to be open to negative angles and know what negative R values mean too. Okay, so let's look at what would, just do this fast. Here's a function, R is a function of theta. R equals 2 sine theta. R equals 2 sine theta. So that's going to give us a set of points, and it's going to give us a graph, okay, a set of points. So here's how we're going to learn to graph that. What we're going to do is we're going to start in rectangular coordinates. We're going to put theta on the horizontal axis and R on the vertical axis, and then we're going to use our rectangular coordinate graph to plot the polar graph. Okay, so R2 sine theta looks like what? So we need to know what sine theta looks like. Does sine theta start at the midline, or the max? Starts at the midline, right? And then as theta goes from 0 to pi over 2, it goes to the max. And the max in this case is 2. Normally it's 1, but we're taking 2 times the sine, right? And then as theta goes from pi over 2 to pi, we go back to the midline. And then pi to 3 pi over 2, down to the min, which in this case is negative 2. And then at 2 pi, okay, so we're going to use this. We're going to use this graph to help us graph the polar graph of R equals 2 sine theta. All right, so watch. So we're going to, look at the polar graph. As theta goes from 0 to pi over 2, what does R do? Increases to 2. So watch the point. So as theta increases from 0 to pi over 2, did you see the point? The point goes from 0 to 2. Watch it again. See that there's a point on there showing you, we need more n values here. try that. Sweeps a little. Shoot. Okay, ready? Watch it. Really help at all. Okay. But do you see that points being generated as theta goes from 0 to pi over 2? R goes from 0 to 2. And so you get something like this. Okay, watch it being generated now. So as theta goes from 0 to pi over 2, we know R goes from 0 to 2. So that's R increasing from 0 to 2 as theta increases from 0 to pi over 2. And then as theta goes from pi over 2 to pi, what does R do? Decreases. So according to the graph, as we go back from pi over 2 to pi, R decreases from 2 back to 0. So it's symmetrically doing what it, or undoing what it did in the first quadrant. So, what does that look like? So, the question is it a circle? Is it a circle or not? We'll find out on Wednesday.